Hi everyone, my name is Yifei Dong. In this presentation, I will discuss our ICRA24 paper, Quasi-static soft fixture analysis of rigid and deformable objects. In this work, we propose a way to characterize the robustness of a challenging class of non-prehensile manipulation primitives through an energy-based metric. The metric indicates how hard it is for an object to escape from its current configuration. Our work can be seen as an extension of prior work on caging-based manipulation methods to the notion of soft fixture. Compared with prior works on dynamic caging problems, our method is able to analyze more general manipulation settings involving deformable objects. Recall that, unlike in force or form closure grasping and immobilization, an object is caged when its movement is merely constrained to a bounded set of configurations. Caging grasps may hence allow limited movement of an object without allowing it to escape arbitrarily far away, like a bird in a cage or a grasped lamp. Caging an object only partially is also a strategy employed by humans in daily manipulation tasks. Compared with prehensile grasping, caging-based manipulation strategies may be especially suitable to handle fragile objects. In this work, we consider rigid and deformable objects modeled as linear linkages and an energy potential function. Our ultimate goal is to determine the escape energy required for such objects to escape from an initial configuration. Formally, escape energy corresponds to a maximal bounded level set of the energy function in configuration space. Let's take a look at the 2D example of a ball containing a point mass and gravity in downward direction. We first consider an energy increase E0 and this sublevel set. The path component of the sublevel set containing x in it is bounded. We then continuously increase from E0 to E1. The path component is still bounded. This still holds until just above threshold E2. Like for E3, the path component then becomes unbounded, but the escape energy is given by the critical energy threshold E2. We call an object with positive escape energy a soft fixture. We consider objects with high escape energy as being robustly contained within the sublevel set. The core challenge we tackle is how to estimate this escape energy in higher dimensional configuration space. Escape energy provides a natural paradigm to estimate the robustness of robotic manipulation primitives. It may find applications also for evaluating gripper design choices. However, we observe that the analysis of global geometric features, such as sublevel set, is challenging. Prior work on caging has often relied on analytic cell decompositions in configuration space, but these methods are not applicable in the high-dimensional configuration spaces of deformable objects. In order to include scenarios with non-rigid objects, we therefore propose the use of sampling-based planning methods as a means to approximate escape energy. While we lose the precision of volumetric representations of C-space, we show that our method is feasible and more efficient for the estimation of escape energy. Let us consider all escape paths of the object. The energy cost along an escape path corresponds to the maximal energy encountered along the escape path. The escape energy then corresponds to the minimum energy cost among all possible escape paths. For example, 2 escape paths are displayed here. Sigma 2 provides a suboptimal path with a high energy cost. Sigma 1, on the other hand, gives the optimal escape path with the minimum energy cost. We observe that the search for the escape energy can be turned into a problem of finding optimal escape path. Such paths raise the potential energy of the object as little as possible during the object's escape. By modeling deformable objects by linkage systems, we incorporate gravity and elasticity into a single energy function. To efficiently approximate an optimal escape path and the escape energy, we proposed 3 sampling-based algorithms. The first 2 algorithms utilize sampling-based motion planners like RT iteratively in a conservative or binary search manner. The third algorithm prioritizes states with lower potential energy. Please check out the details in our paper. We studied the convergence speed and efficiency of the algorithms. We observed that our energy-biased search based on a standard bit star planner converges the fastest. While our algorithms only provide an upper bound estimation of escape energy, we observed that they appear to closely match reference escape energy in experiments. Compared with prior work, the main contribution to our soft fixture work lies in the sampling-based algorithms for escape energy approximation. Together with the generalized formulation of potential energy, this enables a quasi-static frame-by-frame analysis of object manipulation scenarios. Our simulation experiments validate the potential applicability of the approach to novel manipulation primitives, such as manipulating fresh fragile produce or personal protective equipment. These primitives are not amenable to analysis with classical methods such as force closure. In real-world perturbation experiments, we also validated that the computed escape energy estimates correlate strongly with the probability of an object's actual escape.